Okay, good evening, Professor David J. De Los Reyes. Okay, it's a Saturday evening here in Los Angeles, California. So for this session now, I will be bringing out a long video format lecture on alternating current circuit. The topic for tonight will be one of the most interesting topics in alternating current circuits and also in real life because this will now be the computation of power consumption for households enter the world. Okay, so if you know how to compute your power consumption, okay, you got an advantage in the so-called economy because we are paying money for the power consumption, right? So if you could control your power consumption, okay, you are in a good mood. Okay, let's proceed. The topic for tonight will be a long video format discussion, alternating current circuit, lesson number 8. The last time around, I discussed lesson number 7. Actually, lesson number 7 was voltage calculation in alternating current circuits with respect to the impedance load. So, we are through with the knowledge of impedance, the how the current is being consumed by that impedance, the computation of the voltage with respect to that impedance, and for now the topic will be the computation of the powers consumed by an impedance. Okay, let's proceed. Okay, I will try to bring out 1, 2, 3, 4, 4 equations. Okay, under alternating current circuit in general, these are the designations, standard designations of power in the study of alternating current circuit. Alternating current circuit meaning we are getting our voltage from the utility line. So it's an alternating current circuit. That's a real consumption. Okay, let's proceed. For capital letter S, this is capital letter P, this is capital letter Q with the subscript L, this is capital letter Q with the subscript C. Okay? The meaning of this is that S will be apparent power. Okay? And this letter B here is the true power. The one we are paying every month, that's the true power. It's designated by capital letter P. Okay, so take note of this one and the computation of this, because this is the one we are paying every month to the utility companies. Okay, if every time you are taking your power consumption from the utility companies, not unless you got maybe a solar equipment, that will be another thing, right? For Q sub L, this will be the power consumed by any load that contains motor load, something like that. And Q sub C is the power consumption of any load which resembles a capacitance, or it could be a synchronous motor that is overexcited. Okay? Okay, let's try to bring out the formulas on how to compute for the apparent power, true power, reactive power, Q sub L. This L here refers to the inductive load, and this subscript C here refers to the reactive power consumed by the capacitive load. For the apparent power, we got 3 formulas on how to compute for the apparent power. Okay, take note of this. It will be the product of the total applied voltage times the total current consumption. That's apparent power. And the unit of this is actually volt ampere, because the unit of E is actually volt and the unit of I is actually ampere. So the unit of apparent power will be volt ampere, or if you got a multiple of 1,000, So this key here will represent 1,000. This is 1,000. So if you got a volt ampere with the which is preceded by letter K, this is the meaning of this is that kVA, meaning 1,000 volt ampere. And the next biggest thing that is the power rating the apparent power rating is MVA. This M here refers to 10 to the positive 6. That is 1 million. So if you can see a transformer with the rating MVA, meaning the power rating of that one is actually 1 million volt ampere. Okay, so you can see the transformers on the post with the rating, you will not, maybe volt ampere is the ordinary transformer. Hold on. This one, this is a transformer. This is just because this is a small one, it is only rated volt ampere. Okay? But if you got a bigger transformer, which the one you can see on the post, hanging on the post, the rating are actually in kVA. Okay? But for this MVA here, this is very big already. This will now be the power rating, apparent power rating of substations supplying us with current. Substations, the one coming from the power plant. Okay? So this MVA here is the power rating maybe of substations now. This kVA are the power rating of the transformers that is hanging on the post. And this volt ampere is just the ordinary household transformer. It's very small, so the rating is just in the value of volt ampere. Okay, that's equation number 1. Equation number 2, it will be the square of the current times the impedance. If you try to square the current multiplied by the impedance, that is still apparent power. Okay, so take note of that one. That's why the last time around, we have computed I have taught you the concept on how to compute for the current consumption. That's why it is this, right? And the third equation, it will be the square of the voltage, the applied voltage over the impedance. So as you can see, the impedance is actually the one consuming current, right? So the parameter that controls on how we will compute this apparent power is actually impedance. That's why our number 1 topic under AC circuit was impedance. Because without knowing the concept of impedance, okay, you will not understand alternating current circuit. Okay. Number 2, the true power, it is designated by capital letter P. It should be the product of the B sub R times I. Meaning, if you know the voltage across that resistor, okay, then multiply that by that circulating current, okay, you will get the true power consumption, okay, of that resistance. Okay, so the second formula is the first formula is B sub R multiplied by I. The second formula, it is similar to this, but for true power, we are referring to the power consumption of any lighting load. So this will be the square of the current multiplied by R. And the third one, okay, that's why the last time around, I taught you on how to compute voltage across a resistor. So this is a B sub R quantity square over R. And the unit of this is watts. A figure 1, if it is preceded by a letter K, that will be kilowatts. Okay? If that watts is preceded by a capital letter M, that is megawatts. Okay? So this is small, it becomes bigger, this is the biggest. So this megawatts maybe is the megawatts rating of substations maybe. This kilowatt maybe the kilowatt of the transformers that is hanging on the post supplying us with current. And this watts here is just maybe the watts of an ordinary transformer. Okay? This is not even watts, maybe because if the transformer is very small, there is a rating milliwatts, right? Milliwatts. Milliwatts is 1 over 1,000. So watts is actually 1 over 1,000 of milliwatts. This is smaller than watts. So actually the rating of a true power, okay, I will start with the smallest one, milliwatts, watts, kilowatts, or gigawatts. Okay, this is actually the one we are paying on the utility companies. Okay, if we could minimize the true power consumption of our household appliances, okay, we will be saving money. That's why later on our my next topic, that will be the so-called power factor correction. That is where we will minimize the effect of the inductive load and the capacitive load. So what will come out will just be simply, okay, a pure resistive load, and we could minimize our power consumption. And if we could minimize our power consumption, and so with our money paying to the utility company. Okay, for Q sub L. The equations look similar. It is only, the difference is only is that the, what you call this, parameter we are considering for the meantime are different. Because for S, we are referring to Z. And for true power, we are referring to R. And for Q sub L, we are referring to X sub L. So actually, the formula for Q sub L is B sub L times I. Okay, if this is L, this should be L times I. The currents got no subscript. So the current under S, P, and Q are actually same current. It is the same circulating current, so it got no subscript, right? So this is I sub A square times X sub L, or this is B sub L quantity square over X sub L. The reactive power consumption of an inductor will be if you try to square the voltage across C, okay, and divide that by X sub L, that is Q sub L. That is one of the formula. So because actually we got three formulas, right? Voltage and current, square of the current times reactance, the square of the voltage over reactance. For the last one, it is similar to Q sub L, only that the subscript is different. Instead of L, this is C, meaning this is the reactive power consumption of a capacitor, right? So if we try to compute for Q sub C, this first column here looks similar. It should be B sub C times I. Next column, it will be the square of the current times X sub C. The third one will be the square of the voltage across the capacitance over X sub C. This looks similar, this looks similar, then this looks similar. Okay? So in the computation of the apparent power, true power, reactive power for inductance, and reactive power for capacitance, okay, they look similar. Only that for apparent, we are referring to impedance. For true power, we are referring to resistance. For Q sub L, we are referring to inductive reactance. And for Q sub C, we are referring to a capacitive reactance, in which the legend of the capital letters here are actually here. S will be apparent power, P will be true power, Q sub L will be the inductive reactive power. Inductive meaning the reactive consumption, power consumption of any inductive load or motor load. Q sub C is actually capacitive reactive power. And capital letter I is actually the total current drawn, the one circulating on the circuit. Okay, that is capital letter I. Okay, so those are the formulas and how to compute for the four kinds of power. But the one that is, what you call this, very important to us is this capital letter P. And the unit of this is watts, the one we are paying on the utility companies. But if you are a designer, okay, your number one concern should be this apparent power here. Because this apparent power gives us the total power consumption of any system. Because without knowing S, okay, you will not know the total current consumption of any household yours, right? Because if you do not know the total current being drawn by your equipment, okay, you cannot specify the wire sizing of the wires being used on your circuit. Okay, so this is very important for designers. For homeowners, it will be capital letter P because this is the one we are paying to the utility companies. This will be the circuit diagram, same as the last time around, meaning the combination of R, X of L, and X of C is referred to as Z, impedance. That's why the title of the subject matter for tonight is power calculations with respect to impedance. Okay. For the power triangles, there are three possible cases. It will be if the load is inductive, if the load is capacitive, and number three, if the load is a pure resistance. For the inductive load, okay, the power triangle will be something like this. We got a real part, and this is the imaginary part. Okay? So actually, if you try to compute for the value of S, you cannot just add true power with the reactive power because they are different powers. This reactive power is actually 90 degrees with respect to the true power. So you could not add it algebraically. You will add it vectorially. Use your Pythagorean principle, right? Because S will be the sum of the squares of this plus the square of this, then take the square root. Okay, you cannot just add P with Q algebraically because they are different. This is a real true power and this is an imaginary reactive power. So if we try to express apparent power in terms of the true power and Q sub L under inductive load, S will be true power plus J Q sub L. That's the formula. Okay? This Q sub L is an imaginary power, right? So there's a J prior to it, right? So this is a complex power. For capacitive load, there are two variations under inductive load. For a load to be inductive, it's either that the combination is just a combination of R and X of L, right? That will be an inductive load. It's possible also that a capacitance is connected with it, but unluckily Q sub L is greater than Q sub C. So this portion here, instead of just simply Q sub L, it will be the difference of Q sub L minus Q sub C, just in case there is an X sub C, right? But if there is no X sub C, it will just be simply like that. Okay? But if there is an X sub C, but unluckily Q sub L is greater than Q sub C, this portion here will still be Q sub L minus Q sub C. Okay? For the capacitive load, okay, the power triangle will be this. This is the true power, this is Q sub C, and this is S. Again, if you try to compute the value of the apparent power, you cannot just add this true power with this. This is a real part, and this is an imaginary part. So if we try to bring out the formula on how to take the apparent power, it will be S minus J Q sub C. But there are two variations also. Hold on. There are two variations. If the value of Q sub C is greater than Q sub L, okay, this portion here, instead of just simply Q sub C, it will be the difference of Q sub C minus Q sub L. Okay? So if the load is just a pure R and a X sub C, the imaginary reactive power will just be simply Q sub C. But just in case there is an X sub L, and unluckily this Q sub L is less than Q sub C, what will come out for this portion will be the difference of Q sub C minus Q sub L. So there are two variations under capacitive load. Pure capacitive load, or there is an X sub L inserted, but unluckily the consumption of this is less than this. So our net reactive power will be the difference of Q sub C minus Q sub L. Okay, they will subtract. Okay, because they're different. The other one is upward, the other one is downward, so it should be the difference. Oh, that's the second one. The last one, which is the what you call this perfect system. It will be a pure resistance. If the load comes out to be a pure resistance, okay, our power triangle will just be simply a straight line because Q sub C equal to Q sub L rather equal to Q sub C, and this should be equal to 0. It might not be equal to 0, but unluckily Q sub L equal to Q sub C. Okay, if they are equal, they will try to cancel out each other, right? If this is plus 5 and this is minus 5, a plus 5 minus 5, considering for the meantime imaginary part, they will try to cancel out. So this will be gone. This will be gone. So the imaginary part portion of the total apparent power is 0. It is 0. So what comes out for the triangle will just be simply a straight line. So S will now be P plus J0. Okay? This one here, utility companies like it, okay, because we are minimizing the current, okay, being drawn from the power line. Okay, you are helping the utility companies. If your load, it seems just like a pure resistance, okay, utility companies like that one because you are minimizing the current you are getting from the utility line. Okay, so the next topic will handle that solution, but for tonight and how to compute the 3 different powers, it is this. Okay, that's it. S will be apparent power, P will be true power, the one we are paying to the utility line. Q sub L and Q sub C are both reactive powers. Q sub L is for X sub L, Q sub C is for X sub C. Okay, that's it guys. This is Professor David J. De Los Reyes from Los Angeles. Good evening.